We've been talking a lot about synchronization. There are three kinds of synchronization that are commonly used in parallel programs. First of all, there's point-to-point synchronization. This is a pair of post and wait, as we saw, for example, in our there's a pair of post and wait, as we saw in our do across and do pipe parallelizations. There's also a pair of send and receive and message passing. The second kind of synchronization is locks. In locking, you have a pair of lock and lock executed by a single thread. So a thread locks it, then does what's in the critical section, then does an unlock. Only one thread is allowed to be in the critical section at a time, thus enforcing mutual exclusion. This is the way that one can serialize accesses to read-write conflicting variables. The third kind of synchronization that's commonly used is barrier synchronization, which requires that all threads get to a certain point before any proceed. We saw an example of this in our ocean simulation in the shared memory orchestration, where at the end of the iteration, the threads needed to reach a barrier, and only after they reached the barrier were they able to calculate whether the difference was within the tolerance. So why do we need locking? Well, in a parallel piece of code like this, if more than one thread is executing it, what can happen? Threads are adding to the same sum? I think you know that what can happen is that the reads of one of the threads can happen first, and then the calculations occur concurrently, and then one thread stores back its result, and the second thread stores back its result, overwriting the first one. With a lock, only one thread can be inside the critical region at the same time, and so only one thread can do the read, increment, and write. Well, locking is not quite that simple because you need to worry about granularity of locks. If you have a lock that's designed to be only held for a very short period of time, then you can use something like a spin lock where the other processor just keeps testing a shared variable. But if the lock is going to be held longer, you've got to do something more intelligent than that. And so locks vary in their structure according to what granularity is required. And also, we need to consider, and we'll do that when we get to Chapter 9 of the text, how to build a lock that's correct, that doesn't allow two processes inside the critical section in unusual circumstances, and that's also fast, that can check quickly whether or not it can allow a process in, and not do that requiring a lot of cache misses. So those are issues with regards to locks. Now barrier synchronization looks like this. The different threads reach the barrier at different times, but all threads need to wait when they get to the barrier until the very last thread that's seeking the barrier has reached there. This is commonly used in something like the ocean simulation because it works in terms of time steps. In a situation like this, it's important that some threads don't finish way ahead of others, leaving the first ones waiting for a whole long period of time. And that means you've got to balance your load between processors, or this means you've got to balance your load among processors. Execution time will depend upon the execution time of the slowest thread. So what's often done is something called gang scheduling, where you take threads that are communicating with each other and schedule them on processors at the same time. Keep all the other threads off so that the threads that are communicating can communicate pretty rapidly. And then one of the threads doesn't need to wait a whole long time until the other one gets the processor and does what it needs to do to allow the first thread to continue. And that's one reason for avoiding time sharing when you have threads, because if you throw one thread off, then other threads may be waiting on it, so they can't make any progress whatsoever.